Hello everyone. Today we are going to see the physical chemistry revision. So we already done with organic, inorganic. So people whoever didn't see that, please do check it out. We have covered in almost 2.5 hours for entire inorganic and organic. Now physical chemistry, most important formula based numerical questions you can expect. These are the chapters we are going to see today. If you can jump to the chapters if you want, I suggest you to watch it throughout. Okay, so without any further delay, let's get started. First, we are going to start with mole concept. So in mole concept, most of the questions are combined with other chapters. Okay, for example, electrochemistry, chemical kinetics, equilibrium, most importantly redox. So the questions will be combined with these chapters. So point to be noted here is few formulas only. So I'm going to give you the formulas in the real quick. The first thing we have to know how to find the moles. It's nothing but the given mass by molecular mass. Molecular weight, molecular mass, or if they are asking for the gram atom or number gram atomic mass, so anything that would be fine. Given weight by molecular weight. Okay, so once you found the moles, then next step they can ask the questions, find out the number of atoms. So in that case, mass of one atom of element, one atom mass, which is equal to gram atomic mass by Avogadro number. So what is Avogadro number? 6.023 into 10 to the power 23 unit, right? So moving on to the next formula, that is how will you calculate the atomic weight. So if they are not directly giving you the atomic weight, the atomic mass can be calculated as equivalent mass into valency. What is equivalent weight? Equivalent weight is nothing but if there is an acid, how much hydrogen it can donate. If there is a base, how much OH minus it can donate. Or it's depend on the charges also. So the atomic or molecular mass divided by the acids, bases and salts. Okay, so that is what the equivalent weight is. There is another formula to find out the atomic mass, that is 6.4 approx by specific heat. If they are giving these values, you can use it, right? So the mix and match also you can do with atomic masses. If you want the accurate value, you have to put all those accurate values, mostly round of the figure. In the case of MCQs, they will not give you the closest values as options. Okay, then we are going to find the molecular mass. So for finding molecular mass, the simplest formula is 2 into vapor density, right? So either vapor density value they will give, most of the cases they will give. Okay, 2 into vapor density, that is our molecular mass. Our molecular mass of gas, which is mass of 22.4 liters of vapor at STP. If they are not giving us STP, they will give us standard temperature pressure. If that is not, then that would be standard temperature they will give, and the pressure of 1 atm they will give. Okay, so that is about molecular mass of gases. Then for the metals, you can use Dulong-Petit law. So that is not used as much. So I'm jumping to equivalent mass or equivalent weight. So as I told you, equivalent weight, which is atomic weight. If that is for molecule, you just put molecular weight. Okay, then divided by number of electrons lost or gained if that is a redox process, or again atomic weight by, I'm writing it here only, don't get confused, valency of an element, or charge of element, or charge of ion, or acidity or basicity. Okay, that gives our equivalent weight. Then now we are moving to concentration terms. So we may look into it in a redox chapter as well. Redox sometimes, although that is not in the syllabus, it will be combined with electrochemistry and mole concept questions. Okay, so the basic concepts of redox, it's better to know about it, like concentration terms and titration formulas, those things. Okay, in concentration terms, we have molarity, which is nothing but number of moles divided by volume of solution. Volume of solution in liters. Okay, if that is not given in liters, either convert it to liter or multiply into the whole equation, multiply into 1000. Similarly, molality, which is number of moles divided by weight of solvent. Most of the students will get confused over here. Weight of solvent, only the solvent. Okay, the number of moles is also number of moles of solute. Moles of solute. Okay. So weight, which is in kilogram. The next one, which is normality. That is number of gram equivalents of solute. Gram equivalents of solute. Okay, we already know how to find the equivalent weight. So gram equivalents of solute, volume of solution. Once again, that is in liters. Okay, then we know about equivalent weight. How to find gram equivalent? So for finding gram equivalent, we have weight of solute divided by equivalent weight of solute. Into 1000. Okay, if they are asking for milli equivalents, you can put 1000. If that is just for grams, you need not to put 1000. Okay, so the milli equivalents, the same thing, weight of the solute divided by equivalent weight of the solute into 1000. Here the gram equivalent is not 1000, shouldn't be added over here. Okay, once we know this, we do the volumetric analysis, isn't it? So in that case, N1 V1, which is equal to N2 V2. Either of these values they will give, they will ask the another. 3 values they will give, they will ask the remaining one. Okay, the same thing will apply for molarity also, but in this case you should have same solution, or as I can say, it should be of same acid, or but while finding the equivalent number, we'll divide it by some number, no? For acid, for charges, or a number of electrons it lost, that should be of same. Okay, then the next one, which is in terms of molarity equation for the reaction, we have, let's say the reaction is N1A plus N2B. That is giving you the products. Okay, so in that case you need to use m1 v1 by n1, which is equal to m2 v2 by n2. Okay, then mole fraction. So always remember the addition of mole fraction, which should be equal to 1. Let's say I'm taking the mole fraction of A, which is nothing but Na by Na plus Nb. Mole fraction of B, which is equal to Nb by Na plus Nb. So addition of these mole fractions, it can be of 2, it can be of 10, it can be of 100, must be equal to 1. So if they are giving one mole fraction, you can easily find the another one by subtracting it from 1. Okay, then percentage by weight. In that case, weight of solute in grams by weight of solution. Solute by solution into 100 to get the percentage. Similarly, you can do it for percentage by volume, which is nothing but volume of the solute divided by volume of the solution, and percentage by weight by volume means the same thing. Weight of the solute divided by volume of the solution. Okay. Then ppm. ppm is parts per million, isn't it? So how will you find out? That is mass of given solution or given substance divided by total mass of the solution into 10 to the power 6. That will give you the ppm. Okay. Then the next formula, important one, is molarity and to molality conversion. Let's say they have given for molarity and asking for molality. You can use this formula. Molality is mentioned as a small m. Molarity is mentioned as a capital M. Density minus m1, the molecular mass, by 1000. If they are asking it in reverse, I have to do with m density by 1 plus m into m2. Here m2 refers to the molecular mass. Molecular mass of solute, rho is our density. Okay, so these are the important formulas you need to use for mole concepts chapter. So other than this, what else you can expect? You must be able to do the conversions that they are asking. While solving the problems, you will get into it. Don't worry. And what if I missed something? While finding out number of moles, if that is for the gases, you can just use the 22.4 liters. Okay, just multiply into 22/4 liters for any gas. Now we are moving on to the next chapter, that is atomic structure. We are doing very quick, so don't skip or don't miss out any parts. Okay, so in atomic structure, the basic things, the discoveries, discoverers, I'm not going to get into it. Other than this, the definition part, atomic number means we know, mass number means we know, isotopes, same atomic number, different atomic mass, and then isobar, which is having different atomic number but same mass. Then isotones, which is same number of neutrons. Sometimes they will refer that as isoneutronic or isotonic, but isotonic means it can be referred to as different in osmosis process. Then isodiaphers, which is same number of neutrons minus protons count. Same number of neutrons minus number of protons. Okay, so that count is same, that is for isodiaphers. Then isosters, that is molecule with same number of atoms and electrons. Atoms and electrons. Then isoelectronic, which is my favorite because this is asked in many question paper, many examinations, that is same number of electrons. Be careful here with the charges also. Okay, so this is very important. Then moving on to the next concept, that is electromagnetic radiations, EMR. Here the point to be noted is EM waves do not need any medium for propagation, and all EM waves travels with the same velocity. What is that velocity? Light velocity. 3 into 10 to the power 8 meter per second. Okay, so for telling you what is EMR waves, that is a perpendicular waves, right? So here the relationship is more important. The formulas are C is equal to nu into lambda, and wave number, that is 1 by lambda, it is nothing but nu by C, T, which is equal to 1 by V or lambda by C. So for time period you can use the frequency or wavelength and velocity. Okay, so these are the important formulas. You can expect a simple questions from here as well. Then electromagnetic spectrum, as I always told you, always telling you that you can remember it in the order. I gave you the, I remember in the atomic structure crash course, I gave you the order in the mnemonics. Rohit Mishra went to Uncle Xavier's garden, isn't it? So this is the order. You can use radio waves, microwaves, UV, X for X-rays, Z for gamma. Okay, so the wavelength is getting increased when we are moving from here to here, and the frequency is just opposite. So which means wavelength is inversely proportional to frequency, right? Okay, then Planck quantum theory, the important formula is E is equal to h nu. So we also can write that as the total energy transfer, which is ER n into h nu. So this is energy of this particular h nu refers to as energy of one photon. They are asking for total energy transferred then you have to use this formula. Here the N stands for the numbers, right? Number get root number. Then H is for Planck constant. We know Planck constant value is 6.626 into 10 to the power minus 34 joule second. Then photoelectric effect. The points for photoelectric effect is that it's depend on the time, and then the graphs you can look into. Increasing the frequency will not affect the emitted radiation. The intensity matters, right? And what is threshold frequency? Beyond that frequency only the emission happens, right? So E photon, which is equal to threshold energy plus kinetic energy, or you can write it as h nu naught plus kinetic energy. So h nu, which is equal to h nu naught plus kinetic energy. This can be written in the way I am giving you the formulas. Depend on the values they are giving, you can just substitute the values and find the answer. That's it. Okay. So h nu minus nu naught. So these are the important for each line is an important. Okay. Depend on the value they are giving, you just have to substitute it. Then Bohr's model. Bohr's model is applicable for the single electron species only, like hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, sodium 10 plus. So Bohr's model is for single electron species only. That's why they are asking questions in those ions. Then it is related with the particle nature of the electron. It's based on the Planck quantum theory. Okay, so what else the formulas are important? Here you can see MVR NH by 2 pi, right? Or for Bohr orbit, for finding the radius of the Bohr orbit, so you can use the formula R is equal to, these are important guys. Hope you have the formula sheet already. I shared with you at the time of crash course. Z A naught, right? Here N is number of corresponding energy of the orbit. Z is atomic number we know, and which is mentioned in Armstrong. Okay. So other than this, if they are asking for velocity of electron, then V is equal to 2 pi k Z E square divided by NH. In the simplest form, you can write it as by substituting the constant values Z by N meter per second. In case of centimeter, then that will become 10 to the power 8. Okay. Then potential energy formula, which is equal to minus kz E square by R. Potential energy, where is that? R is infinite and potential energy is 0. Then comes the important shortcuts to find the values. If they are asking for total energy, then for any species like hydrogen-like species, then you have to go about total energy or hydrogen into Z square for same orbit, if they are asking. If they are not asking the same orbit, if they are asking for the same transition, Then delta E, transition means the change in energy, how much it left or released, right? The delta E of hydrogen-like species, which is equal to delta E for hydrogen into Z square for same transition. Okay, so energy of nth orbit. Energy of nth orbit for hydrogen-like species, again, most of the questions you can expect like this. Hydrogen-like species only. E1 by N1 for same atom. Then they may ask you the questions about ionization energy, which we have discussed in periodic properties, right? Then we are going to spectrum. Spectrum, we have hydrogen spectrums, is it? So Lyman, Balmer, Paschen, Brackett, Fun. So Lyman is any orbit to 1. So I'm taking n infinity to 1. Any orbit. Okay, so n any to 1. This is n any to 2. This is n any to 3. This is n any to 4. Fund is n any to 5. The one more thing important over here is which region this is observed. Sometimes they will not give you the name of this series. They will give you this is observed in UV region. This is observed in visible region. Like that the question can be given. So in that case the first one is UV, the second Balmer is visible. The remaining are infrared region only. Okay. Then Rydberg equation, which is very important. Whatever the examination you are writing, this question you can expect, which is 1 by lambda RH Z square 1 by N1 square minus 1 by N2 square. So if I am substituting the lambda values and nu bar with velocity, then I would write it as RH Z square, the same thing. Okay, from the given values you just do the mix and match. So what is the value of RH is that 1096.78 centimeter inverse. Then the maximum number of spectral lines. This type of question can be asked. Maximum number of spectral lines. So in that case, n is equal to n2 minus n1, n2 minus n1 plus 1 divided by 2. So maximum number of spectral lines for Lyman series, the lines for any series, that is n2 minus n1 only. Okay, then our de Broglie equation. Okay, so one more thing I wanted to tell you, that is total emission lines. So that is, which is n2 minus n1, n2 minus n1 plus 1 divided by 2. Okay, so the same only, the alpha line, first line, starting line, initial line, it also always referred to as first line of any series. The last line, limiting line, margin line, it is referring to last line of the any series. the total number of the line in the sample of atom, which is N2 to N1. That is our transition. So the total emitted lines, which is N into N minus 1 divided by 2 for N to 1. N into N minus 1 by 2. Okay, so moving on to de Broglie equation. Lambda, which is equal to h by mv or h by p. M stands for mass, v stands for velocity, p for momentum, and h for Planck constant. Okay, so other than this, lambda, which is equal to h by root of 2m k for kinetic energy, that will also be works on the solved form is 150 by v Armstrong. So if the electrons are solved, if the given values are solved, then you will get ended up with this formula. V is a charge of the particle as related by the potential. This type of question can also be expected. These two formulas are super important. Then Heisenberg uncertainty principle. So which states the position and the momentum can't be found simultaneously and precisely, isn't it? So this is the formula. They can just ask the correct notation. What is the correct formula? Or else they will give you the values and ask you to find anyone. The another version is that x is equal to m delta v 4 pi. Okay. Then comes our quantum numbers. Quantum numbers are, I'm telling you in simple words, principal, azimuthal, magnetic, and spin. Okay, so if I am taking 3 p electrons, okay, so 3 refers for principal. Principal is nothing but the shell. P refers for azimuthal, which is subshell. SPDF orbitals, no, that is our azimuthal quantum number. So for S 0, P value is 1, D 2, F 3. So azimuthal is referred as the symbol L, principal is N, magnetic is M, spin is S. So what about magnetic quantum number? That is 0 minus L2 plus L. For example, here I am having L value 1. So this will be minus 1 to 0 and then plus 1. Okay. Spin quantum number, it's always having a 2. That is minus 1 by 2 and plus 1 by 2. Because in a shell, we are writing 2 electrons, right? So one is clockwise, another one is anti-clockwise. The minus 1 by 2 and plus 1 by 2 refers that. So as simple as that. So what else can be asked from quantum number is that they will ask you which of the following is making sense and find out the quantum number, those type of questions. I have given you the formula. Other than this, they will ask you about angular momentum, orbital angular momentum, which is equal to L into L plus 1 whole root into h by 2 pi. right? H is our Planck constant. So for hydrogen and hydrogen-like species, all the subshell of a shell can have a same energy. Okay. Then the rules to filling the orbits, we know. Alpha principle, where they are referring this kind of snake structure, you might have seen this, right? Then n+1 Borbary rule. The subshell with the lowest n+1 value should filled first, right? And the next rule, that is Pauli's exclusion principle. What that it refers, it states the 2 electrons in an atom can have a same values of all 4 quantum numbers. Then Hund's rule of maximum multiplicity. You have seen this enough in coordination chapter, isn't it? So which states the electrons are distributed among the orbitals of the subcell in a way to give maximum number of unpaired electrons with a parallel spin. Okay, these 4 are remains for filling of electrons. There was some very easy question asked in a question paper, previous year paper, asking for which of the following rules is used to, which is odd one out. That kind of question have been asked. So you can expect a easy question from this part as well. Then talking about the shape of orbitals. Shape of orbitals, we have S, P, D. Most importantly, we have S for spherical, P is double shape, D is double. Right. So this is the shape, and in P we have 3 categories: Px, Py and Pz, right? So where we have along the axis, in Y also we have it along the axis. In case of D, we have 5, that is dxy, dyz, dzx, dx square minus y square, and dz square. Among these, xy, which will have between the axis, and this one is also between the axis, dx square minus y square, which will have along the axis texture. Let's say I'm having y and x over here. So the double shape will look like this. Okay. For dz square, the shape is bit interesting. That is, in z-axis I'm having the cloud, and there I'm having an electron cloud over there. Okay, so that is our z square of d orbital. So some questions asked in which is along the axis, which is between the axis, that type of questions. Okay, here you can expect about nodes. What is nodes? Where we can find the electron density 0. The probability of finding an electron is 0. So nodes can be of 2 types: radial node and angular node. So radial node, the formula is n minus 1 minus L, and the angular node, that is just equal to azimuthal quantum number. Okay, some questions can be asked finding total number of nodes. Total number of nodes means you have to add these. While adding this, what will you get? L will get cancelled out. Remaining n minus 1 is your total number of nodes. Okay. So if they are giving you this type of picture and asking you for number of nodes, so how can you find it? This is a graph between R square and R. Okay. So this is for 3 yes. So 3 is the nodes. If you are substituting 3 minus 1, right? Total node is 3 minus 1, that is 2. You can see the cut over here on the axis. So that gives the number of nodes. Okay. So I'll give you the picture of 3p also, or I can give you the 2s, which will have only one cut over here. So that refers 2 minus 1. Here also I'm getting answer 1. Okay. So probability distribution is talking about this. It's a function that gives the probabilities of occurrence of different possible outcomes of the experiment. Then you know very well about the exceptional configurations like for copper, chromium, niobium, molybdenum and dose list. Okay. So here we came to the conclusion of atomic structure chapter. And one more thing if I want to tell you, that is half a fully filled electronic configuration is more stable than the half filled configuration and comes partially filled or randomly filled. Not random, it's like it's not half, not fully filled, that kind of arrangement. Okay. So these two are much more stable. Okay. Now let's move on to chemical bonding. Very easy chapter. You can expect questions from here as well. So chemical bonding talks about the different types of bonding and the reasons to hold the bond, why it is strong, why it is weak, like that. Right. So first, the conditions for chemical bonding, the attraction should be more, right? Here the question can be expected from Lewis octet rule. Every atom to try to attain a 8 electron configuration in the outermost orbit, which is an nearest inert gas configuration, by donating, gaining or sharing of electrons. Right? There are some exceptions too. We'll see that. The exceptions of Lewis law, which is electron deficient molecule. Electron deficient molecule, like in the case of BeF2, BeCl2, BH3, BF3, AlCl3. So these are some electron deficient molecules. These are stable, but still they are not having less than 8 electrons. These are having less than 8 electrons. That is first exception. The second exception is that electron rich, then 8 electrons. Those are like IF7, SF6, PCl5, XeF6. So these are some examples of more than 8 electrons in the outer electron shell. Then the third one is odd electron molecule, which is of NO, ClO2, NO2. These are some which are having odd number of electrons in their valence shell. Okay. And helium, lithium, hydrogen are never obeyed octet rule also. Okay. So then we are moving to types of bonds. you very well know about types of bonds, which are ionic, metallic, covalent, coordinate bonds. Okay, I'm going to give you which is strong and which is weak bond. What is the order? The strong bonds are ionic, which is attraction between two ions. Covalent is formed by the sharing of electrons. It's almost strong enough, equal to coordinate. Coordinate is the donor is only one atom, only one element which will become a donor, and which means both the electrons are donated by the same element. Then comes our metallic, where the pool of electrons or sea of electrons holding the bond stronger. These are some strong bonds on the order. What about weak bonds? So weak bonds, which is of hydrogen bonds, van der Waals, Debye and dispersion forces. Hydrogen bond, we'll see some examples, which is more stronger among the weak bonds than the van der Waals. Okay, so these questions can be asked. And so let's see the properties of ionic bond, ionic compounds first. Okay, the questions can be asked from this part. As I told you, this is an attraction between cation and anion, the bond between metal and non-metal, except lithium, magnesium and those parts. Still, the electronegativity difference must be greater than 1.7. Okay, and the metal should be large, ionization potential should be low, and the size of the non-metal should be small, electron affinity should be more, and the lattice energy should be high. Okay, so what are the energies involved in bond formation? Delta H, which is equal to our SE, I'll tell you what is SE, IE plus D by 2, right, minus EA plus U. So which is the first category, that is total energy observed minus total energy released, right? So this includes lattice energy, ionization potential and heat of atomization, everything. These are the details we got from Bohr-Haber cycle and lattice energy, right? So some questions can be asked to find out the energy, total energy, how much, or lattice energy calculation also. Then the properties of ionic bond, the physical state, that will have a strong electrostatic force of attraction, right? And then ionic bonds are more stronger than any other bonds. In solid form, it's a bad conductor of electricity or bad conductor of electricity, and in aqueous or molten state, that conducts or good conductors of electricity. Then this shows isomorphism, which is nothing but two compounds are said to isomers when they are having a similar number of electrons in it. Say for example, NaF and MgO. So total number of electrons over here, that is 11 plus 9, 20. Here 12 plus 8, 20. So the same number of electrons. Okay. Then, okay, the next thing, solubility. Solubility, the ionic compounds are soluble in polar solvents like water. Soluble in polar. And factors affecting solubility, here we have dielectric constant, which is directly proportional to solubility, and lattice energy, which is inversely proportional to solubility, and hydration energy, which is directly proportional to solubility. So for any compound, if that is have to soluble in water, then hydration energy must be greater than lattice energy. Okay, so the question can be asked in the way to find out the lattice energy and tell me which is soluble or not. Okay, and the important point is that no compound is 100% ionic, and every compound contains some kind of covalent nature as well. Because of its strong electrostatic force of attraction between cations and anions, it becomes the two ions and covalent character is developed. That's what we are calling it as polarization. So the covalent character is directly proportional to polarizability or polarization, which is directly proportional to effective nuclear charge of cation. And what are the factors affecting polarizability? That is charge of cation or anion, inversely directly proportional to polarizability, and size of cation is inversely proportional to polarization and inversely proportional to covalent character. And next one, size of anion. Size of anion, which is directly proportional to polarization and covalent character. Then pseudo inert gas configuration, which is having a 18 electron in the outermost shell, have more polarizing power. Then it's because of effective nuclear charge. Then what are the bond theories we have? There are two bond theories which is important, that is VBT and MOT. VBT talks about hybridization and shape. So I already gave the list of which hybridization belongs to what shape. I have already given that. You can make a note of it, or it's given in your book as well. The molecular orbital theory, it is an imaginary concept, but still it could explain the magnetic nature and existence of species which is having the fractional bond order. Okay, so the point to be noted for MOT is that there are two type of two category where we have writing it. The number one type, that is bonding, another one is anti-bonding. Okay, so while finding bond order, we are using 1/2 bonding number of electrons minus anti-bonding electrons. Right, so that will give bond order. Bond order which is directly proportional to strength, bond strength, which is inversely proportional to bond length. Okay, then there are two types of writing it. So one is the electrons is less than or equal to 14. The another type is electrons is greater than 14, electron is less than 14. So there are two types. So where the changes is that the electrons are less than 14, less than or equal to 14, everything seems okay till 2s. Then in case of 2p, the order goes like this: 2px, 2py, 2p, sigma 2p z, then comes pi star 2px, pi star 2py, and sigma star 2pz. So this is how the electrons must be filled. In case of the another category, as I told, till 2 years that is completely fine. In case of this, the problem starts with 2p, sigma 2pz, then comes pi 2px, pi 2py, then pi star 2px, pi star 2py, then sigma star 2pz. Okay, so this is the order of filling the electrons for the next type, O2, F2, N2, Ne2 type. Okay, then the next one, that is VITEEE theory. VITEEE theory we already discussed in detail. We have posted the list of with mnemonics also. If you want just to comment it over there, I'll share the PDF once again. Anyway, that is there in our PDF list also. Okay, so this gives us a lone pair and bond pair geometry. Okay, so how to find the shape geometry which is used by VITEEE theory. So you can see, I will give you a simple example, which is NO2 minus. Okay, so how will you do that? The valence electrons of nitrogen, which is 7, so the valence electron becomes 5 for nitrogen, plus oxygen, the valence electrons are 6, so 2 oxygens are there, 6 into 2, the overall charge is minus, so I'm adding plus 1 electron. I'm getting 6 into 2, 12, 12 plus 6, 18. So if the number is more than 8, then you have to divide it by 8. If that is equal to or less than 8, then you have to divide it by 2. Here that is obviously more than 8. So 18 by 8, 2 as a quotient, 2 as a remainder. 2 is less than 8, so divided by 2, which will become 1. So 2 bond pairs, 1 lone pair must be there. So 2 plus 1 combination, which will be V-shape angular. Okay, that is the shape of NO2 minus. And the hybridization, which is the combined of 2 plus 1, that is sp2. Okay, similarly you can work upon other examples also. For every example this works. That's it about this chapter. Now we are moving on to thermodynamics. For thermodynamics, we already dealt with the detailed explanation in the crash course. We are going to have a real quick with the formulas only. Let's start with enthalpy. So enthalpy, which is denoted as H. So H is equal to, which is nothing but the total heat content of the system at constant pressure, isn't it? So H is equal to E plus PV. Or they are asking for the change, then that would be delta E plus P delta V. If they are having different pressure conditions, then you can use P1, P2 also, which will be delta E plus P delta V, V delta P. Okay, at constant pressure this formula works. If that is both the things are varying, the second one will holds good. Then if they are talking about the number of moles, then delta E plus delta Ng RT. So what is delta Ng? Which is number of products, number of moles of products minus number of moles of reactant in gaseous state. Then first law of thermodynamics, which states neither be observed nor be emitted. Then Q is equal to delta E minus W, or you can write it as delta V, which is equal to Q plus W as well. Here Q can be either observed or evolved also. Positive for observed and negative for evolved. Then what is isothermal process? As the name indicates, this is temperature constant. So which makes dT, which is equal to 0. So if the dT 0, delta E, which will also become 0, and Q, which is equal to minus W. Right. So this is important. It's true for ideal gases only. Ideal gas only. Then the second process, that is adiabatic process. Adiabatic, where Q is equal to 0, then delta E, which is equal to W. Right? The internal energy you used up to work done by the system. If the work done on the system, then the internal energy will get increased. Then the next process, that is isobaric process. Isobaric means pressure constant, where dP, which is equal to 0, so that QP at the heat at constant pressure, which is equal to delta H. So here we have few important formulas. The first one is for irreversible process. For irreversible process, W is equal to P external into delta V. For reversible process, W is equal to integrated P delta V from V1 to V2 state. Okay. So the third one, that is reversible isothermal. Reversible isothermal. Isothermal, I have told you already, temperature constant. Right. So the W, which is equal to minus 2.303 nRT log V2 by V1. Or you can take the pressure also, which is P1 by P2 you should take. Okay, pressure and volume are inversely proportional. Then the fourth formula is for adiabatic. Adiabatic process, which is W equal to delta E. For ideal gas, I told you that is W, which is equal to NCV, that is molar heat capacity at constant volume, T2 minus T1. W, which is equal to NR gamma minus 1 T2 minus T1. When an ideal gas is freely expanded in vacuum, then the obtained work done is 0. Okay, so which is noted, P external becomes 0. Ideal gas expands freely. Okay, then reversible expansion processes are more efficient than the irreversible process, irreversible expansion. Okay, so these are the points, these are the questions can be asked, but mostly for the common entrance examinations, they will ask on the simple part only. Then talking about entropy. Entropy is just a randomness, right? So which is denoted by the symbol S. So for the delta S, for reversible isothermal process, which becomes 2.303 N or log V2 by V1. So we know that delta S, which is Q reversible by T, that is the general formula, and this is for reversible isothermal process. Then if they are asking for delta S of products and reactants given, then just subtract the values. Asking for total delta S, which is system plus surrounding, isn't it? So plus system plus surrounding delta S value. There is another formula also for delta S, which is Q by T of system. They are not giving directly the delta S value of system and surrounding. You can just get it from heat and temperature. Okay, so other than this, for a reversible adiabatic process, delta S becomes 0. Reversible adiabatic, delta S becomes 0. For entropy of fusion, change of fusion, delta S, which is equal to delta H by T. T is a freezing point or melting point. If they are asking for the vaporization, then that will become delta HV divided by T. T for the boiling point. Okay. Then standard entropy means the entropy of 1 mole of the substance at 1 atm and 25 degree Celsius. Then we are moving on to free energy. So free energy, which is nothing but the we are taking as a G for Gibbs. G, which is equal to H minus Ts. What else the formula we have? That is delta G, which is equal to delta H minus T delta S. Or if they are asking for the products and the reactant, then G product minus G of reactants. Right? Then delta G naught of an element, which is always 0, and delta G naught they are giving for K rate constant, then you have to use log K. 2.303 or log K. K is equilibrium constant. So there is a table I'm giving you here. The most of the questions from this part is a combination of this table. Okay, so here we have delta S, delta H, and the combination of this and the behavior. Okay, so the first one, which is delta H is negative, delta S is positive. Then delta G becomes negative. This is spontaneous reaction. You might have seen many questions in spontaneous and non-spontaneous processes. Delta H is positive, delta S is negative, then this will become positive. I mean the delta G become positive, and this is non-spontaneous process. Then delta S is positive, delta H is also positive, then delta G becomes negative if H is greater than T delta S. delta G becomes positive when H is less than T delta S. So if that is negative, then that is spontaneous. If that is positive, then that becomes non-spontaneous. There is another category that is both are negative. Then once again, delta G is negative for delta S is greater than delta Ts, and the process becomes spontaneous. And delta G, which is equal to positive if delta H is less than T delta S. Okay, so these are the questions can be asked from this chapter. Next we are moving on to equilibrium. Let's start with equilibrium chapter. Here we have two types of equilibrium, that is chemical equilibrium and ionic equilibrium. Let's start with chemical equilibrium, where it states the law of chemical equilibrium is very simple. Here we have A moles of A plus B moles of B, which will giving us X moles of A and Y moles of Y. Okay, so we very well know about the equilibrium, those stuff. I'm not getting into that, why this is symbol, those parts. The formula which is important, that is Kc, which is equal to concentration of product X raised to the power the molar coefficients, and then Y raised to the power of Y divided by A raised to the power A, B raised to the power B. That is for Kc, which is equilibrium constant. Okay, in terms of concentration. In terms of pressure, again the partial pressures of X raised to the power X, partial pressure of Y, partial pressure of A, partial pressure of B. Okay, so what is the relationship between Kp and Kc is that Kp, which is equal to Kc into RT power delta Ng. Delta Ng we very well know, which is number of moles of product minus number of moles of reactants. If there is more than one, we have to sum it, right? So that is what the formula is. This relationship itself as a straight question which was asked in previous year paper. Okay, what are the factors affecting this? Catalyst never affect anything. Okay, it just do the motivation, that's it. That is what the work is. Okay, then the important part comes here. These three. The question can be twisted in these part. I think one more will also be there. Let's see. The first one, if the reaction is reversed, then the equilibrium constant is inversed. Okay, reaction. Let me take the different color. So reaction is reversed. Then equilibrium constant is inversed. The second one, if the reaction, the reaction is divided by the factor. Reaction is divided by a factor n. Then we have to take the same factor root. Okay, if that is divided by 2, then we have to take square root. Okay, then the third type, which is the reaction is multiplied by the factor. Multiplied. Then you have to raise it to the power of the factor. And the fourth point is that if that is having number of steps, then the equilibrium constant will be the multiples of equilibrium constant in the each step. It goes up to Km. Okay, if that is having a multiple step. Clear? Then we are moving on to effect of temperature. This formula is important. Just they will give you the value, substitute and tell me the answer. The calculation itself big, so they will not much twist the question. Just the equation that is important. Then reaction quotient, which is very similar to our reaction concentration Kc value, but where that is similar, You can see the equation is pretty simple, which is similar to Kc, but Q value becomes equal to Kc at equilibrium only. If Q value is less than Kc, then the reaction proceeds in forward direction. Okay, if Q value, reaction quotient value, which is greater than Kc, then that proceeds to backward direction. Okay, so this part also can be asked as a question. Then free energy, delta G values, the equilibrium constant, reaction quotient we know. Here now we are coming to free energy change. Delta G, which is equal to delta G naught, standard free energy, plus RT ln Q. Q is reaction quotient. In terms of Kc, you can have a formula like this. Kc equal to 1 means delta G naught equal to 0, where the reaction which is in equilibrium. Then another possibility is Kc is greater than 1. Then the delta G is negative, the reaction is spontaneous, and that is forward direction. And delta G naught, which is positive, means then that goes to backward direction. Okay, clear? Then we are moving to Le-Chatelier principle. I just cut shorted and giving you the essence of Le-Chatelier principle. Le-Chatelier principle, which is nothing but just a balancing method, right? If salt is less, we are adding salt, that's it. If that is an equilibrium reaction, the concentration of the reactant increases, then it proceeds to, reactant increases means it have to be decreased. So it will proceed to forward so that more product will be formed, reactant will get decreased. Then product concentration is increased, then that will go to backward direction. Okay, then coming to temperature factor. Temperature increases. See, endothermic, exothermic, there are two type of reactions. Endo means absorbs, heat absorbing reaction. Exo means heat evolves. Okay, if already it needs more heat, if you are supplying more heat, it will proceed to the forward direction. If that is already evolving the heat, still you are applying heat, means it will not proceed forward, it will go backward. If the temperature decreases in exothermic reaction, then it will go to forward direction. Pressure factor. Pressure. You can remember pressure and volume factors by PV is equal to nRT. Ideal gas law, you know, right? So pressure increases means number of moles. Where the number of moles are less, that side the reaction will go, because more the amount of pressure means volume become less. So it doesn't want that, so that it will go in the direction where the number of moles are less. Then the pressure decreases means that where the number of moles are high, then that will go to that reaction, that direction. Okay, that is as simple as that. You can expect in many questions from, questions from Le-Chatelier principle. Okay, what are the factors are not affecting it? Catalyst, inert gas addition, constant volume, it will not affect. What about constant pressure? At constant pressure, it moves towards larger number of moles, more number of moles. Okay, so these are the factors don't affect. As I told you, catalyst will not affect, inert gas will not affect, constant volume will not affect. Then we are moving to ionic equilibrium. Ionic equilibrium means there are two types of ions, two types of electrolytes. One is electrolyte and non-electrolyte. Electrolytes are the one which can melt and conduct the electricity. Non-electrolyte which will not conduct the electricity. Our main concern here is that electrolytes only. Electrolytes can be divided into two parts, strong and weak. depend on what? Dissociation. So if the dissociation is more, then that is strong electrolyte. If the dissociation is weak, then that would be weak electrolyte. Dissociation is nothing but how many ions are willing to get separated. If the HCl is a strong acid, because while we are dissolving it in water, it will become H plus and Cl minus ions very easily. They want to get separated. Okay. So alpha here, that is dissociation constant. Okay. So alpha becomes 1 for strong, alpha becomes less than 1 for weak electrolytes. Then acid-base concept. So these gentlemen who said which is acid, which is base. There are 3 types of theories. The first one is Arrhenius concept, where he is saying acid is a substance which is a proton producers, which produces proton. For example, HCl, H2SO4, HNO3, HBr. So those are proton producers. And the base, which is the one which are OH minus producers. We are saying NaOH, calcium hydroxide, ammonium hydroxide, potassium hydroxide. These are bases. That is for Arrhenius. Brownstedt-Lowry said acid is a hydrogen, the H plus donors. Okay. Arrhenius was saying it is a producers H plus. It is Lowry is saying that is H plus donors. What is the difference, ma'am? So these are protogenic substances which should be able to dissociate the H plus and donate it. HCl, acetic acid, these are. And the base concept is different. H plus acceptors. Here comes our NH3. So which will become NH4 plus. Isn't it? So H plus acceptors they are. Then the third concept, that is Lewis concept, which is very, very, very important. The first one, all 3 are equally important, but Lewis is bit more. So Lewis acid says electron pair acceptors. Acid is electron pair acceptors, which means there should be an empty orbital. The Lewis octet rule, no? Whoever that is having the deficient electron, that exceptional case will come here. I told you when I just taught you about Friedel-Crafts alkylation, acylation, and those electrophilic substitution part. There should be an empty orbital to produce an electrophile, right? So these are the Lewis acids. Then Lewis bases are electron pair donors, like ammonia, which is having lone pair in it. Like water, that is lone pair in it, F minus. So these are some Lewis bases. The question can be asked, which of the following is Lewis base? Which of the following is used acid? So that you should be aware of that. Then common ion effect, which is very simple. There will be a suppression of degree of dissociation of weak electrolytes when we are adding a strong acid to it, okay, which is having a common ion with it. This is just a concept, the suppression of dissociation. Then there are 3 types of salt hydrolysis. The first type is weak acid and strong base. It is an anionic hydrolysis and having a alkaline solution, which is pH more than 7, right? For the formula for finding hydrolysis constant, Kw by Ka. Okay, then degree of hydrolysis, H is equal to Kh by C, and pH formula is also given. Okay, then the second category, strong acid plus weak base, cationic, pH is less than 7, acidic, then Kh, that is hydrolysis constant, Kw by Kb, degree of hydrolysis Kh by C. both are same. Then pH, which is equal to, find the signs, which is minus. There it was plus. Okay. And here that is B, Kb. Okay. The third category, weak acid and weak base. They are having anionic and cationic both. Neutral pH, pH is equal to 7. Ka, which is equal to Kb in this case. And hydrolysis constant, which is Kw into Ka into Kb. H, that is her degree of hydrolysis, is root of Kh only. pH is pKw plus pKa minus pKb. Okay, minus pKb. There is no log C over here. Then the next one is solubility product. There are these type of salts. For example, AB type. AB type is AgCl, P2, BaSO4, the same amount of cation and anion. Okay, that is AB type. That is 1:1 type. Binary electrode, where the solubility and Ksp relation is that S is equal to root of Ksp, which also can be written as Ksp, which is equal to S square. Okay, then ternary electrolyte 1:2 type, AB2 type, where Ksp value which is equal to 4S3. And ternary electrolyte another type is 2:1 type, A2B type. The values are pretty same. And another type, A3B2 type, it is 108S5, S to the power 5. Okay, so these formulas will be used to find out the solubility product, solubility kind of problems. Then coming to buffer part. What is buffer first of all? If you are adding a little amount of acid or bases, it maintains the pH. The pH will not change much. Right. So there are buffer is a solution which is mixture of two. There are certain buffers, acidic, basic, simple and mixed. We'll see the examples one by one. The mixture contains equimolar amount of weak acid and its salt with a strong base. For example, if I'm having sodium bicarbonate with carbonic acid and sodium acetate with acetic acid. These are acidic buffers. Similarly, in case of basic buffers, the mixture will contain the amount of weak base and its salt. For example, ammonium hydroxide is weak base. Its salt is ammonium chloride. Okay. Then simple buffer. Those are weak acid and weak base in water, like CH3COO, NH4 or NH4CN. These are, and proteins and amino acids, mixture of an acid salt and a normal salt of a polybasic. So these are some simple buffers. What about mixed buffers? This can be of acidic and or basic. Okay, these are type of buffers. So mostly they will concentrate about acidic and basic, because the question can be asked from numericals also. These two are the important formulas to find out acidic and basic buffer pH. Sometimes they will give you basic buffer values and asking for pH. Okay, then we know that pH plus pOH, which is equal to 14. So subtract it from 14, find out the pH. Okay, the buffering capacity means the number of moles of acid or base added to the 1 liter of buffer. I told you, right? Buffer is something when we are adding acid or bases, the pH will not change much. So how many number of moles of acid is added? What is the slight pH change you just observed? So if that is more, then the buffer capacity will get decreased. If that is less, the buffer capacity is good. Okay, then more importantly, Oswald's dilution law. This is for weak electrolytes. Weak electrolytes means what? Where the alpha value is less than 1. Correct. So where I'm having K is equal to C alpha square by 1 minus alpha, which is an important formula you can use for this type of questions. Okay, so that much about the chemical and ionic equilibrium chapter. Now we are moving on to the next chapter, that is kinetics. Kinetics very simple, very few formulas, but you can expect a question from this chapter. Kinetics is very simple. How speed the reaction goes, that's it, right? So if the rate of disappearance means the product is getting reactant is getting decreased, right? So that case the minus symbol will be given. Disappearance means it is getting decreased, means minus symbol. Appearance means produced, then plus symbol will be there. Okay, simply if we are not mentioning it, that is plus. So dA by dt. So that is the difference of appearance and disappearance. Then next one will be order. So order of the reaction. This is defined as the total number of reacting molecules whose concentration determines the rate of the reaction, or we can say the total number of reacting molecules whose concentration changes during the chemical change, which is getting changed during the chemical change. That's what the order is. Okay. So in general, the order of the reaction is defined as, how we are writing it, is just a sum of powers to the which the concentration terms of the reactant must be raised to the order to determine the reaction rate. So mostly the questions can be asked in the statement type or in the numericals. dx by dt, which is equal to k a to the power x and t to the power y. These are found out by the experimental methods. Okay, so order of the reaction with respect to A is x. Order of the reaction with respect to B, that is y. So total order of the reaction means we have to sum it, that is x plus y. So what are the factors affecting it? That is temperature effects, catalyst effect, and the nature of the reactant will also affect the order of the reaction. So what are the types of the order of the reaction is there? The first type is zero order reaction. So for example, this photochemical reactions, H2 plus Cl2, the presence of H nu, it will give 2HCl. So these are zero order reactions. The integrated rate equation, which is concentration of A at time t, at concentration of A at initial time, which is equal to, minus KT, T for time. So T half, that is half-life, which is A naught by 2T. That is one zero order reaction. First order reaction, K and T half is given. First order reaction is super important among these order of the reactions. Then activation energy. One more thing I want to tell you, that is unit of order of the reactions. The first order reaction, the unit is S second inverse, and the zero order reaction, the unit is mole L inverse S inverse. Okay, so I just make it very simple to get more marks. That's why I skipped second order and third orders. Now we are moving on to activation energy. We already made a video of detailed chemical kinetics crash course. If you want more, you can watch that video as well. Activation energy, which is if an energy want to happen, reaction need to happen means there should be a collisions. The only those collision in which the colliding molecules possess certain minimum energy, which is called our threshold energy, right? We saw it like we saw in the photoelectric effect. This excess energy, if that is possessing, that will be supplied to the reactant molecules in order to raise them to the level of threshold energy. That is what we have calling it as activation energy. The excess energy possessed by the molecule. So K, which is equal to A, activation energy, E exponential raise it to the power of EA RT. Here A is pre-exponential factor, EA, that is activation energy, R is rate gas constant, and T is temperature. Okay, just substitute the values, you will get the answer. Those type of questions only they will ask. Then temperature coefficient, mu, which is equal to K T plus 10, temperature plus 10 degrees by K at temperature. Let's say they have given 273 to 283. Okay, so those that is our temperature coefficient coming into picture. Then factors affecting activation energy, that is catalyst and nature of the reactant again. So what are the factors affecting rate of the reaction is that concentration, pressure, catalyst, exposure to radiation, nature of the reactant, of course, physical state. Those are affecting the rate of the reaction. Then finally we have collision theory. As I told you, some kind of collision must be happen that should have enough energy to make that it proper. So those are having threshold energy, and also the proper orientation of the collision is also important. Here you can see the reactant starts over here and reaches the product level. The graph is between energy and reaction coordinate. The first one is without catalyst, and as a duty of the catalyst, what that have to do, that will reduce the threshold energy so that more molecules can pass through and form the product very easily. So this is the graph represents that. The important formula over here is how to find the threshold energy, which is equal to potential energy plus activation energy. Delta H, that is H, the enthalpy of product minus enthalpy of the reactant. Okay, so that's about our chemical kinetics chapter. Let's move on to solution chapter. Solution and colligative properties. Mostly in solution chapter you need to know around few formulas, that's it. Okay, so in solution chapter maybe they will start with this molarity, those concentration terms. We have covered it already. So now I'm moving on to the real solution part. First one is Raoult's law. Raoult's law, what that it states, it is for the volatile components of A and B, right? So PA, which is equal to mole fraction of A and the pressure of pure A. Similarly, you can write it for PB as well, mole fraction of B, and pure B, pressure of pure B, vapor pressure of pure B. If they are asking for total pressure, then PA plus PB You can just substitute the values as well here to get the total pressure. We saw these were volatile components. So what about non-volatile solute? So non-volatile solute, for that we have P naught minus Ps, then P naught, which is equal to N2 by N1 plus N2. N1 and N2 are number of moles of 1 and 2. You can just substitute it with given mass by molecular mass as well. Ps is for solute, pressure of solute. Then osmotic pressure, which is pi equal to CRT. C is our molar concentration, molarity. Then R is gas constant, T is our temperature. Mostly the gas constant value here we are using it is 0.0821 liter ATM Kelvin inverse. Okay, sometimes they may use our normal, what we are using, 8.314 joule per Kelvin per mole. Then the next concept is, I told you, isotonic solutions, right? Isotonic solutions have same osmotic pressure and same molar concentration. If one solution has lower osmotic pressure, it is hypotonic, which means lower osmotic pressure, and hypertonic, which is higher osmotic pressure. Okay, so the more concentrated solution is said to have a hypotonic with respect to the dilute solution. Isotonic means both the solutions are having equal osmotic pressures. Then its colligative properties. The first property, that is elevation in boiling point. So here I am having the formula delta TB, what is the difference in boiling point, into ebullioscopic constant into molality. Okay, not molarity, molality of the solution. In the next formula, that is depression in freezing point, that is delta TF equal to KF into M. KF is molar depression constant, and M is again molality. The third one, which is our lowering of vapor pressure. Before that, I would like to tell you the relationship between these two. If they are asking for KB, which is equal to RTB square by 1000 into LV. LV is our latent heat of vaporization per gram, which can also be replaced with delta HV also. Okay. Similarly, if I want to write it for KF, then 1000 into LF or delta HF, latent heat of fusion. Now comes the third colligative property, that is lowering of vapor pressure. So lowering of vapor pressure is adding a non-volatile solute to a solvent is due to the converting up of partially the surface of the solution by the solute particles which are non-volatile. And the fourth property, that is osmotic pressure. So there is a factor which influences this colligative property. That is our Van Hoff factor. Van Hoff factor. So what that is? Van Hoff factor is nothing but denoted by I. I is equal to observed colligative property versus calculated. Calculated means theoretical. So you can write it as M calculated by M. Sorry, not M. M for molecular mass. Okay, so observed value by calculated value. So molecular mass of calculated by molecular mass of actual or observed, you can write. Which because colligative property which is inversely proportional to molar mass. Okay. So now how it affects. So for the solution which are undergoing dissociation or association, then there comes our Van Hoff factor. TB which is equal to I, that is Van Hoff factor, KBM. Similarly, TF, delta TF equal to I, KF into M. For osmotic pressure also, I, NV by RT. Okay. So C only I have replaced with NV by RT. Molar concentration I told you, right? Then if the solute is undergoing association, then I value becomes 1 minus alpha plus alpha by N, which is equal to alpha is equal to 1 minus I by 1 minus N, which I can write it as N minus 1 by N. Van Hoff factor is greater than 1 for the solutes which are undergoing dissociation, and it is less than 1 for association. Greater than 1 for dissociation, and which is less than 1 for association. So other points need to remember in this chapter, which is the common salt or anhydrous CaCl2 is used to clear the snow on the roads, which will decrease the freezing point so that the ice will get melted easily. Remove snows. And then ethylene glycol. Ethylene glycol, which is added to water in the radiator to lower the freezing point. These are some application based of this chapter. That's it about. And one more thing, that is Henry's law. Henry's law, where we are talking about mass of gas dissolved, which is proportional to pressure of gas above the solution. Okay, imagine any carbonated drinks bottle. Okay, the mass of gas dissolved, which is directly proportional to pressure of the gas of the solution. So we can write that as chi A, which is equal to Henry's law constant into pressure of A. Similarly you can write it for solution B as well. Okay. So that's it about this chapter. Next we are moving on to electrochemistry. Let's say electrochemistry, it starts with the basic metallic conductors and insulators and electrolytic conductors. So the conductors, we have the basic classifications and the definitions which we already know. Moving on to the electrolytic conductors, which flow the electricity takes place with the decomposition of the substances. This is produced because of movement of ions. Okay, movement of ions. As the temperature increases, the electrolytic conduction is also increases due to the dissociation, where the resistance happens because of inter-ionic interactions and viscosity of the solvent. Here the Faraday's law is followed. Okay, so that is the difference. What is Faraday's law then? So Faraday's law is nothing but W equal to Z into I into T. So W is how much substance is deposited, and Z is electrochemical equivalent, I is the current, and T is time seconds. So mass of the substance, how much is deposited at an electrode, directly proportional to the quantity of electricity passed through an electrolyte. That's what the Faraday's first law says about. The equation is important. You just have to use it. Then the second law says the mathematical expression of how much the X is deposited and Y is deposited. The ratio of X and Y deposited, which is equal to equivalent weight ratio of X and Y. That is our Faraday's second law. Then product of electrolysis. So the first one, at molten NaCl, you can see the anode and cathode reactions over here. For aqueous NaCl, what is the anode and cathodic part? These can be asked as questions. For dilute H2SO4, for concentrated H2SO4, how this is getting dissociated. Okay, so these are important. Then we are moving on to the conductance parameter. First one is specific conductance kappa. It is a reciprocal of specific resistance of a solution of 1 centimeter length, which is having a 1 centimeter square of area of cross section. The mathematical form is L by RA, and the unit is also important over here. Can be the simple questions asked from this part. Then equivalent conductance. The definition is conductance of the ions produced from 1 gram equivalent of the electrolyte kappa into V. That is 1000 by normality is given. Then molar conductance, just for 1 mole of an electrolyte in a given solution. Once again, kappa into V, that is kappa into 1000 divided by molarity. So how the conductance is varying with the concentration. The first one is molar conductivity. How the strong electrolytes changes, which can be defined by the D by Huckel-Onsager equation. This equation is super important. Delta M, which is equal to delta M infinity, molar conductivity at infinite dilution, minus B root C. B is a constant specific to the electrolyte type and C is a concentration. Okay, so note down this formula and use it when they are asking you questions related to this. And the point to be noted here is the strong electrolytes like KCl show only a small increase in conductance with dilution. This is because they are already completed the dissociation into ions and all concentrations. So the dilution is only reducing the ionic interionic distances between interactions, which will hinder the ion movement. Okay, so the real part of electrochemistry starts over here. Coleridge law and its application, where the limiting molar conductivity of an electrolyte. This formula, this question was asked in previous year papers. So ionic conductivity of cation and anion, we have to sum it to find the molar conductivity, which can be used for acetic acid, HCl, in these methods. For finding the degree of dissociation, alpha is equal to delta C m by delta naught m. Let's move on to electrochemical cells. So electrochemical cells converts between the chemical energy to electrical energy, right, which is nothing but the redox reaction, anion and cation part. Oxidation, which is the loss of electron, and reduction, which is gain of electron. There are mainly two types of electrochemical cell. One is galvanic cell, another one is electrolytic cell. Galvanic cell, where the spontaneous conversion of chemical energy to electrical energy happens, and anode part oxidation occurs, cathode part reduction occurs. So what is the difference between electrolytic cell and the galvanic cell is that galvanic cell spontaneous and electrolytic cell is non-spontaneous conversion, which requires more energy from externally also. And in electrolytic cell, anode part is a positive terminal, cathode part is a negative terminal, but remaining the reactions are same, oxidation and the reduction occurs in anode and cathode respectively. The Nernst equation, which is very important in electrochemistry chapter, I am writing it over here, which is E cell equal to E naught cell minus 0.0591 divided by n log Kc. Okay, or else you can put the Kc value as well. At equilibrium, this E cell value becomes 0. So at end you will get 1 by n log Kc only. Okay. Then we are moving on to the application part. So how we can predict whether the reaction is feasible or not, spontaneous or not. The first thing is oxidizing and reducing agent strength. More positive indicates the stronger oxidizing agent. More negative indicates the stronger reducing agent. E naught value is so important. Then E naught cell, positive E cell value indicates the feasible reaction, and negative E cell reaction indicates the non-feasible reaction. Okay, and we also know about this electrochemical series, which will gives us the displacement, how the displacement happens, whether the displacement happens or not, that kind of information. In the type of cells, where we have primary cell, that is dry cell, where the anodic reaction and cathodic reactions are given. It is used in portable electronics and flashlights. Mercury cell, anodic and cathodic reactions, which is used in watches and small electronic devices, which we are not using it now. The second one is secondary cell, which is a rechargeable cells, like we used to have in the UPS or any rechargeable devices, our phone. Lead storage battery, which is nothing but our UPS, and during charging this reaction gets reversed. Okay. Then nickel cadmium cell, that is used in emergency lighting and portable electronics, which is having a long life duration. Then fuel cells, which converts the chemical energy from fuel directly to the electrical energy. The continuous operation as long as the fuel is supplied. This is having high efficiency among all and environmental friendly as well. These reactions are very important in fuel cell. Please go through it. Anodic and cathodic reactions are given and the overall reaction as well. It has an efficiency up to 60%. It requires less maintenance. The key differences between these three types of cell is this is primary cell is one-time use, simple construction and affordable, and the secondary cells are reusable, higher initial cost, more economically long-term. Fuel cells are continuous operation, requires fuel supply and highly efficient. Then the important formula, that is ionic mobility and transport phenomena. So unit of ionic mobility, which is centimeter square, volume in volt inverse, second inverse. Size effects. How it affects the ionic conductivity is that smaller size generally show lower ionic conductivity due to the extensive dissolving property. This might have seemed counterintuitive first, but when we are considering that the smaller ions attract the larger spheres of water molecules, their effective size matters. Then in the special case of H plus and OH minus, these ions exhibit unusually high molar conductivity compared to other ions because of their Groth's mechanism, where the proton jump from one water molecule to another water molecule rather than moving through the solution of the whole ion. This equation is pretty important in case of transport numbers, which will tell you the fraction of total current is carried by each type of ion. Then what is salt bridge and liquid junction potential? These are uses can be asked in the statement type of questions. So the specialized electrodes and their application, the first one is metal ion electrodes, zinc, copper and silver. Amalgam electrodes, which is having zinc amalgam with zinc electrode, provides the more stability. And the gas electrodes, these are used in the inert metals to facilitate the gas reactions. Mainly platinum with hydrogen and H plus as a hydrogen electrode, Cl2, Cl minus as a chlorine electrode along with platinum. Okay, platinum here serves as a catalyst. So these three are metal insoluble salt ion electrodes. Calomel electrode, lead sulfate electrode and silver chloride electrode. These electrodes measure electron transfer between the different oxidation states of the same element, which is the redox electrode, which is our hero of this chapter. So you can see the formula over here, efficiency, which is given by delta G by delta H minus NFE by delta H, which will give us the ratio to total energy change can be converted to the useful electrical work. For example, here you can have a reaction of zinc concentration cell and gas concentration cell. The E cell value, which is 0.0591 by N log C2 by C1, where C2 is greater than C1. So other important formulas of this chapter is the type of reaction prediction, delta G, E values, and the type of cell. So if that is given, how will you predict the type of reaction? So if I'm having delta G negative, E value will become positive for galvanic cell, means this is spontaneous reaction. And if delta G is positive, then that will become negative. This is an electrolytic cell. Mostly I am telling you delta G value predicts a product. By seeing the delta G value, you can say delta G is negative means that is spontaneous, delta G is positive means that is non-spontaneous. If that is 0, then that is in equilibrium. Then the type of cell would be dead cell. Other than this, we have cell potential formula, which is delta G naught, which is equal to minus NFE E cell. Or you can write it as, also write it as minus 3.303 RT log case. Okay, so that's it about this chapter. We have pretty much covered everything in this chapter. So please do practice more and more questions. I'm attaching the mock test question papers in the description box or the first comment. Please do check it out and attempt those questions to know where you're lagging. All the best for your examinations. Let me know if you want any other concept to be discussed, any other video you want. Thank you.